So let's discuss the concepts of work and kinetic energy. Of course, when we mean work, we don't mean sitting at a computer like this. We actually mean the physics definition of work. And we've mentioned work before. Work can be a force times a displacement. It can also be looked on as a change in energy. And this is where we're going now. Instead of looking at things in terms of forces and displacements, we're going to look at things in terms of powers and in terms of energies. And in some cases, when you're lacking some values, or in some cases, using an energy argument can be simpler than employing kinematics, as we have done so far. And it's sort of a choice in some cases as to how you proceed, as to what's easier and more intuitive. But let's talk about work. The work done on a system represents the energy that transfers into or out of that system, meaning that the transferred energy can be given by the change in energy. Delta E is equal to the work. The energy of the system is basically a combination of some potential energy and kinetic energy. Remember our previous definition of work that we just discussed. We can look at work as a change in energy. We can also look at work from the basic physics perspective, that work is a force times a displacement. If we move mass 1 from at T1 to position 2 at T2, then our work is our force times this displacement S. Work is equal to F times S. Now we do have to be somewhat careful when we look at this. Here we are displacing this mass in the x-axis, and as such that means we can only combine a force in the x-axis with a displacement in the x-axis. Now we've decomposed forces many times before, and here we have a force at some angle theta. The only component of the force that can be put with S here is the F cos theta component. We can only take the S displacement with the F component of force. We could not here simply say work is equal to F times S. We would have to, in this case, say work is equal to F cos theta times S. So the directions are important when defining our work. Work, however, does return a scalar quantity in Newton meters. So as we just said, work here is force times displacement, or for the case that we're looking at here, work will be F delta x, or F cos theta, the force in the x direction, times delta x, which essentially is our displacement S just in the x direction. And it's best to look at every situation and figure how you should solve the problem. Which direction is displacement? And after you know which direction the displacement is, you can find the components of the force that you need to put with that displacement and usually solve the problem. But when we talk about work, sometimes we have variable forces, sometimes we have constant forces. And remember, when we're applying a force to something, we're usually applying an acceleration to it. Now, if we look at a force position graph, which you should really think about here, force position, where work is equal to F times S. That means a force position graph, an Fs graph, this would be F, this would be S, will basically give you the work done if you look at the area of the curve. So if we have a constant force acting on our system, then the area of this graph will be force times displacement. Sometimes displacement can be given as d, distance, or s, displacement, or delta x. Here, area is force times displacement, which is going to equal work. So really, this is the basis of calculus. Work will be force times displacement, or force times x2, our final position, minus our initial position. And remember, this is displacement, so it's a movement from one position to another, where it ends up versus where it starts, not the total distance traveled. But taking the integral of your Fs graph will give you W, work. Now, with a variable force, that could be slightly more complex. As you could see from any basic calculus, if we look at the F versus S graph here, we would have to sum all of these various elements, which basically is an integral over our function. So for a constant force, that wouldn't be particularly difficult, as we saw before. It would be a nice flat line against F versus X, and we could just find the area under it with a simple geometric relationship. Quite often you're given some kind of work function or force function versus x, where you would have to take the integral of that particular function. You could even in some ways do this from an acceleration if you knew what the mass of the object was. So if you were given an acceleration function, you could essentially look at the acceleration and displacement and then multiply by mass. So our work really turns into an integral over our force function. Here our limits would be our displacement x1 to x2 of fx dx, which of course is just the area of our curve. So if you have a variable force, then you would have to perform this particular integral, as simply just saying f times s would not give you a straight answer particularly. You do have to be rather careful with varying forces, and most problems that you see will tell you whether the force is variable or whether it's a constant force acting on the system. But we'd be remiss if we did not mention the units of work. Work, of course, was defined as delta E, an energy change, and any energy is basically given as 1 joule, and of course that is 1 Newton meter. We're looking at a force times a distance, Newton meters. So the joule is usually the unit that we will use, and you'll see values in joules, kilojoules, maybe even megajoules for some cases, especially when you start to deal with electricity in future physics courses. You might even see gigajoules. But if we are looking at, say, atomic physics, which frequently people do, then a unit of work is referred to as the electron volt. Now I realize that people see electron volt and think voltage. Well, voltage is related to the amount of work that's done by a charge, but we're not going to sideline everything and get into the discussion of electricity here. But 1 EV, if you see this value, 1 electron volt, is equal to 1.6 roughly times 10 to the negative 19 joules. And this is a unit you will frequently see if we're, say, talking about the work done on a particle, such as an electron or a proton. So any sort of molecular or atomic calculations tend to refer to electron volts instead of straight joules. It's often preferable to just work in joules if something is in EV and convert this. This would of course be given to you as a conversion in the exam should you need to use it. But please bear this in mind, that the electron volt here is a unit of work. It's in joules. It's an energy. So we've defined energy as E. We've said that we can look at delta E being work, but we haven't really gotten into talking about energy in depth. As we said, there are kinetic energies. Kinetic energies basically being movement energies. Any moving object will possess a kinetic energy, and that kinetic energy will be equal to half the mass times the velocity squared, 1/2 mv squared. There are many types of potential energy that we will discuss, and we will discuss when we talk about such things as conservation of energy, the transfer of potential to kinetic energy when we reach that point. But right now, let's take a look at the moving objects. When we look at moving objects, we're dealing exclusively with kinetic energy, 1/2 mv squared. So at its most basic, we can take a look at a vehicle, such as this Humvee here, which has a mass m. It has a mass of 3,000 kilograms, and it has a velocity of about 25 meters per second. It will move here from the left to the right in the positive x direction. So the most basic calculation you could see would be 1/2 m times 25 squared. 1/2 the 3,000 times the 25 squared should give us about 937.5, or about 938,000 joules. 937.5 times 10 to the 3. Now I realise that's a very basic substitution, but get an idea here of what kind of kinetic energies you should see back for typical things like vehicles travelling down the street. Something I said when we discussed things like displacement and velocities. Make sure you're getting the idea in terms of joules as to how much energy vaguely a system like this should have. And this kind of Humvee here driving down the street, 3,000 kilograms, 25 meters per second, should give you somewhere in the regions of tens of thousands, hundreds of thousands of joules. But the kinetic energy of this particular vehicle comes from the work that's done on it. In order to keep moving, work has to be done. You have to be sitting in this vehicle with your foot on the accelerator, providing a constant driving force. We've talked before about how friction and air resistance will eventually stop your vehicle from moving. So we're saying that this is going to be d, the distance, will be velocity times time here. So a constant force is required to keep our mass moving, to counteract the forces of friction and air drag and keep F consistent. Of course, we could move at a constant velocity, right? If we have F equals ma this way and we have a force of friction this way, our accelerations could cancel and we could move at some velocity. So, in terms of our equations, if we're looking at the work done on any mass, we could say that A would be F over m. Acceleration, of course, in this particular case, if we started out at v equals 0 with an initial velocity of nothing, would just be Vf over t. This essentially is Vf minus Vi over t, where Vi is 0. If we ignore friction for the moment, A equals F over m is equal to V over t. This means the work done on our mass, Fd, will equal mass times acceleration times displacement. Substituting in for these values, here's our acceleration, here is our displacement essentially. What we'll end up with is mv squared over 2, or 1/2 mv squared is equal to our ke. And that's the proof of why we have kinetic energy being equal to 1/2 mv squared. But what does all this really mean? This means to give any object a kinetic energy, to increase its velocity or to keep its velocity going, we have to give it work. So to give an object kinetic energy, we have to do work on it. And as you can imagine from things we've looked at previously, we'll be using F equals ma to do that, to provide the force component here. Of course, every time we use F equals ma, or as you could see from the previous equations, anytime we use displacement or velocity, we're probably referring back to our equations of motion. So this is the work energy principle. If we're going to do work on something, we're going to change the energy of the system. And this is what we were saying at the beginning of our talk here, that the work done on a system really represents how much energy is going into or coming out of that system. Transferred energy changes the system's total energy by delta E, which will be equal to how much work we've done. And of course, our E will be some potential energy term and some kinetic energy term. So in terms of kinetic energy, if our mass is staying constant, our task is usually to figure out what V is, of course, or what F could be. And of course, this means manipulating our equations of motion. So acceleration from this equation, V squared equals Vi squared plus 2as essentially here, can be rearranged to find our acceleration. So this is a situation that's under a force and will have some initial velocity, some final velocity. So we've done problems like this in the past, that we don't necessarily need to force F equals ma when we can use the values that we have. Perhaps we need to use V here to find A. Perhaps we can use A to find V. But we can relate the work and the kinetic energy of our system, of course, by saying work is equal to F times S, where F is equal to ma. Work, of course, is also given as a change in energy. So sometimes you don't necessarily need to engage with F equals ma and do complicated things with acceleration to backtrack your equations of motion. In many cases, you can just define your work as a change in energy. So if we know what Vf is, and we know what Vi is, and we know that the mass remains constant, we can make the statement that work is equal to half mvf squared minus half mvi squared. So work is delta Ke, a change in energy. So Kef, our final kinetic energy, minus our initial. So we can express this as acceleration, of course, if we looked at the V's, but we could also do a straight calculation in terms of energy and find our work value in joules without any conversion. So if we're to look at a calculation involving kinetic energy is half mv squared. Our vehicle will start out with some velocity Vi and end with some velocity Vf. If the car's moving, say, at 25 meters per second, which is about 55 miles per hour, which for a little Fiat like that is probably quite fast, the mass of the car is 1,000 kilograms, let's say. So kinetic energy here is 1/2 times 1,000 times 25 squared. And like I said, keep an eye on what kind of values you're getting. So about 3 times 10 to the 5 joules. If we're to look at delta Ke for this case now, which is really what our work is, then our change in kinetic energy, if we started off with a velocity of 0, as we did in this case, will simply be the final kinetic energy. So if we're being explicit, we'll say work is delta Ke equals 1/2 1,000 times 25 squared minus 0. Of course, this would be implied as we go through the problem to give us 3 times 10 to the 5 joules. So, a typical question might be worded like this. A car moves for 25 meters. The work done now by the car's engine is 3.125 times 10 to the 5 joules. So what is the force on the car? And this often causes people confusion, and they tend to not want to convert between, say, discussing energy and discussing force, even though work is delta E, but it's also delta S times F. So using work equals Fs, we've got a 25 meter displacement here, and we know the work done in terms of the energy here. So work is F times S. We're going to say that F is W over S, the work divided by the displacement. That will give us 3.125 times 10 to the 5 over 25, which will simply give us 12.5 times 10 to the 3 newtons, or about 13,000 newtons. This is a relatively simple problem in terms of a rearrangement, in terms of thinking. What often happens is people tend to have in their heads an idea of how to solve a problem in terms of F equals ma, and a problem, or how to solve a problem in terms of energy. Here we're mixing it up. We're using an energy here, our delta E, with work, and dividing it by a displacement to get back a force. This is perfectly acceptable. Just make sure you know you can do this, that you know this trick exists, and you know what's referred to here essentially as the work energy principle. That we can go back and forth between a work which is involving a force and a work which is involving an energy. They're interchangeable in this case through the formula W equals Fs. So as stated previously, if we have a constant acceleration, or we have a variable acceleration of course, we can look at whatever our function is, and the F versus X curve will give us the work on that particle, which in those cases would be some kind of integral, essentially a summation over the path of Fs. Now, this kind of integral is usually a path integral, which means it's what's going on with S that usually changes rather than F. So let's change gears a little bit. That wasn't supposed to be a joke about using vehicles. Change mental gears here and think about work and force here. And sometimes you can reason things out without even engaging with an equation. So here we've got a fridge that sits in the bed of a truck. So this fridge is sitting in the truck bed. And we're going to have a force of static friction between the bed and the fridge. Somebody didn't tie their load down. And it's just that static friction that's going to keep this fridge from sliding out and causing a major road accident. The work done on the box, which is essentially the fridge, by static friction as the truck moves from the right to the left, will be, so we have to stop and think about this, A, will it be positive? B, will it be 0? Or C, will it be negative? Now this truck is moving in this direction with some acceleration. We're going to have a mu s here, we're going to have some coefficient of friction, and of course some frictional force, which is going to hold this fridge in place. This means the truck is moving from the right to the left. Its displacement, essentially, in our terms, is negative. What does that mean for the direction, essentially, of the force of friction holding this thing steady? So, work is equal to F times S. Which direction is the force here? Which direction is the acceleration here? Do I have to do the Jeopardy music? Da, 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 da. Oh, you could just skip slide. The answer here, as we're moving in a negative direction, is going to be that the work done by this fridge, or the work done by friction acting on this fridge, is positive. Please convince yourself of why this is the case, and there are many examples that discuss this, and here we actually came to this conclusion without even engaging with a formula and writing it out. We could of course look at work equals F times S and look at the work done by the vehicle versus the work done holding the fridge steady. So we don't just look at, say, a moving object like this and look at friction. If there's a force involved, then work must be done and energy must be exchanged. And one of the concepts we need to look at here is the concept of Hooke's law. And we briefly touched on this when we talked about resistive forces. Now with resistive forces, essentially we're looking at a block which is attached to a spring or some mass on a spring with Hooke's law, which is extended by some distance x. Now Hooke's law here, this equation, obviously came from Robert Hooke, who we've discussed before in the context of gravity. F of x here is a force essentially in the direction that the spring is acting, and often you'll see F is equal to negative kx. Sometimes this spring can be hanging in the y direction. There is not a separate equation that says F equals negative ky. The coefficient of friction in the y direction is actually lower than x. That's a joke. Ignore that joke. It's bad taste. But fx equals negative kx. This means that f can be in the x or y direction. F is equal to negative kx. So work is equal to the integral of f dx, the area under the fx curve. Now, if we look at a system with a spring, the force of the spring is negative kx. This is going to restore your system to its original position. So given a spring here attached to this wall, attached to this block, we can grab this block and we can pull it. That'll give a spring extension. The spring will want to pull this block back to some equilibrium position with a force of negative kx. That means if we want to hold this object at this given position, we'd have to put some force on it, like hold onto it with your hand, and provide a force of positive kx to hold this spring in place. This means if we actually plot a graph of f versus x, and this is really what Hooke was doing in order to come up with his equation, you would end up looking at this graph and the work done by the spring would end up being this area. So why am I talking about the work done by a spring? You might say we've just discussed work, Dr. Horn, you mercurial polymath. Well, we have just discussed work, but there's a very specific equation that comes from this, and as you can see in this linear relationship for the force on a spring versus its extension, we end up with this triangle. And that means that the work done by a spring equals 1/2 k delta x. What's the extension of the spring squared? 1/2 k delta x squared. So x2 here is whatever the length the spring ends up at. x1 is its original length. So work for a spring has its own special definition that is not just work equals fs, it's work equals 1/2 kx squared. And Hooke's law is often used in these cases. So here we can see we have an equilibrium point and we have our spring, which is going to have a force on the system. If the system is left alone to sit at its equilibrium length, F is equal to 0. If we extend the spring through some distance x, then our force will act to return it to equilibrium. So negative kx here gives a negative value as x is positive. Here we're looking at the force returning again the object to equilibrium. So once again, F is negative kx. This case, the positive is as x is negative. So we end up with positive and negative forces that oppose the negative or positive displacement of our spring. This means that our force, because it's restorative, doesn't matter whether you're this side of the equilibrium or this side. You always end up with an equation of F equals negative kx. And that means the work that's done by a spring always gives us minus 1/2 kx squared, the area of the FS graph. And this is worth remembering. So x1 and x2 are essentially the positions that our spring starts at and ends up at. Now, compare this graph to the form of the previous graph, which was in the positive axis. If you take this mass and you let it go, it will spring back and forth, back and forth, back and forth. That means the system will oscillate. It will move either side of an equilibrium point. That means for an oscillation of a mass on a spring, you'll end up with some relationship like this. So this is the force, this is the extension. Essentially, this will be extension xi, xf, system bouncing back and forth. That means we can look at an area 1 here and an area 2 here in the case of the work done. F times S for each part of the oscillation. And that's kind of the proof of Hooke's law. If F equals negative kx by Hooke's law, we can perform an integral instead of messing around with taking empirical data and plotting out a graph. So work here is Fx, which is negative kx dx. Integrating this and taking the constant out gives us x dx, or negative k xf squared over 2 minus xi squared over 2. So the work done by the spring, as found by Hooke, becomes half k ix squared minus half k xf squared. Or the work done is the two areas summed, or the subtraction of them, which gives us 1/2 kx squared minus half kx2 squared. So that's where that comes from. What you really need to know is the result of this, and the fact that the work done by a spring has its own specific formula when compared to, say, the work done by moving or displacing a mass from one point to another. So let's take a look at a problem. So here we have a 0.4 kilogram block that's pushed along a frictionless surface, and here we have this function of v equals vxi times negative 0.5 in the I direction, so in the x direction. This is given in unit vector notation. PowerPoint doesn't like the hats. It then runs into and compresses a spring which has a spring constant K of 750 newtons per meter. So remember, when you're talking about stretching a spring or compressing a spring, as you stretch or compress that spring, it will inflict a force per meter of extension. So the more you extend the spring, the more force you will get back from it. And that should make sense from what you should have observed from springs in pretty much everyday life. If you stretch a spring, the further you stretch it, the more recoil force it has, the more force it has to want to return to its original shape. And it will do that as long as you stay within what's called the elastic limit, and as long as that relationship between force and extension stays linear. And that's true within that limit. So, back to the question. 0.4 kilogram block, here's our function along the frictionless surface in its velocity, and here's our value of k. The block runs along the surface and then it hits a spring. It's stopped by the spring, but it's going to take some compression of the spring to take away the energy from the block, and that energy from the block will go into compressing the spring, and the energy will be stored in the spring. So the question is, when the block is stopped by the spring, how much is the spring compressed by? And there's our situation. Block with velocity v hitting a spring. So the work that's done on the block by the spring force is going to relate to the displacement of the block. So delta x will be x2 minus x1. The work done on a spring, remember, is half kx squared. So what we essentially have here is half kx1 squared minus half kx2 squared. Now, I'll point something out here, that this work is equal to a delta ke essentially, or not so much a delta ke, but a change in the energy stored in the spring. We said work was delta E, here we're looking at it as a displacement and essentially an energy. So, in this case, as the force from the spring equals the net force, then the work of the spring is related to the kinetic energy of the block. So the block's initial kinetic energy is going to come from half mv squared, and then when it comes to rest, it will then be 0. It will come to rest when the spring is compressed to its maximum distance. So the block's going to come in with some velocity, hit the spring, translate its energy to the spring, and come to a stop, a v of 0. So we can say that the kinetic energy of the block will be ke2 minus ke1, which is half kx squared, the work done by the spring to stop the block. So we'll have 0 minus half mv squared is equal to negative 1/2 kx squared. We wanted to know the extension, or in this case, the compression of the spring. So that means a rearrangement of this relationship. Of course, this goes away, gives us x2 here will have a magnitude of the root of mv squared over k. Substitute in. We know the mass, we have the velocity, we have our 750 here for K, newtons per meter, this will give us 1.2 times 10 to the minus 2 meters, which of course is about 1.2 centimeters. Or, more realistically, a negative 1.2 centimeters, a compression of the spring of 1.2 centimeters, or 1.2 times 10 to the minus 2 meters. So let's take another look at another example, slightly ridiculous, but here I just guessed the mass of a hedgehog. Here we have a cartoon hedgehog, for you gamer people out there, that's running into a spring of force constant K of 6,750 nanometers. Nanometers? Newton meters. I keep doing that. Be careful. Don't do that. Do as I say. Don't do as I do. 6,750 Newton meters. How much work needs to be done to compress the spring by 0.5 meters? Well, Sonic comes in, hits the spring, compresses the spring. Now, as we just said in the previous example, as he hits this spring, he's going to come in with a kinetic energy of half mv squared and impart that energy to the spring. That's going to do work. Work compressing the spring will of course be half kx squared. We know he's going to compress this spring by 0.5 meters in this case. That means we have the constant k. We can say this is equal to 1/2 6,750 Newton meters, got it that time, times 0.5 squared, which will give us 843.75 joules. That's the work done compressing the spring. Now, I had to guess the mass of a cartoon blue hedgehog, so please, there might be a slight error in that, but given that he would have a mass of about 50 kilograms, how fast was Sonic running to compress the spring by 0.5 meters? Well, what do we know? We know that he compressed the spring by 0.5 meters and the work done by the spring was 843.75 joules. That means that was the energy imparted to the spring. If he comes to a stop, and of course we're neglecting friction and inefficiencies, we can safely say that the kinetic energy that Sonic brought into this system was equal to the amount of energy that went into compressing the spring. So our kinetic energy here is 1/2 mv squared, which is 843.75 joules. So, if this is our kinetic energy, all we have to do is rearrange here and say that V then is 2 times 843.75, essentially being our kinetic energy, over the mass, which will give us 5.8 meters per second. Not particularly fast, but here we're dealing with a hedgehog. So, this is a thing you can do in terms of making equivalencies between energies and essentially the work done to a system. The work done to our system in this case was the work done by the spring, going to compressing the spring, of 1/2 kx squared. The kinetic energy he brought to the party was 1/2 mv squared. So our equation essentially in terms of energy would be 1/2 kx squared equals 1/2 mv squared. And then you can rearrange for v and get an answer. This might seem obvious when you're presented with it in this sense, and it kind of is, but when you're presented with a fresh question and no clues to help you out, quite often people will start to do F equals ma and compare that to say F equals kx, then get into a mess trying to find acceleration and then stick it into an equation of motion to get v. That could in some cases be a valid solution, but as I've always said, the simplest solution is usually the one that gives you the best answer. It takes less work and it means you're less likely to make mistakes with a simple calculation. So, if you look at it and it seems to be a complicated problem in this case to do kinematically, it might be leading you to the idea that this should be done in terms of energy and in terms of work, even though you might be asked for fundamental things such as velocity and acceleration. So let's look at some specific cases. And one of the more confusing cases for people is usually forces that do no work. Now this should not be confusing because there's a very simple reason for this. Think back to our equations. When we looked at our equations, work was a force times a displacement, or a change in energy. Now we haven't discussed the potential energy and the conservation of energy yet, but we will do. When we are looking at, say, a gravitational energy, it's usually a force times a distance, in which case this usually turns into gravitational energy of mass times a height, mg times h. That means if the height of an object above the ground, essentially, that's under the action of gravity, does not change, then the work put in does not change, and then its energy does not change. Additionally, if work equals Fs, if S is 0, then an object actually does not do any work, or no work is done on that object, more correctly. So take this kind of situation. Here we have a very blank weightlifter, but he's lifting this weight through some distance S. But then when he gets to his destination, i.e. gets this weight above his head, he can then essentially lock his elbows, and as long as he's strong enough and his bones don't crack, he can hold this object stationary above his head. Now I realise anyone who's lifted weights is probably saying, well, I'm grunting and groaning and sweating and it's really hurting, don't tell me I'm not doing any work. Well, you're still putting a force in, a force against that of gravity, mg is acting down. But as long as you're providing that force and you are counteracting the force of gravity essentially, mg downwards, you're holding this thing completely still. That means your displacement, or the displacement here of the mass on this barbell weight, is equal to 0. So if S is equal to 0, work is equal to F times 0. So if an object undergoes no displacement, even while the force, especially while the force is acting on it, no work is done. So next time you're holding some weights and you're holding them stationary and it's really hurting, just remind yourself that you're not actually doing any work. Mentally it might help, or it might not. But still, from the physics perspective of work is equal to force times displacement, in this case, while this person is holding this weight stationary, S is equal to 0. No work is done in this case. The other case where we can say no work is done, case was not supposed to be a joke in this particular context, is if we're looking at a force that's, say, perpendicular 90 degrees to our displacement. And this is a very common error on things like exams where people are trying to plug numbers into a formula. They see a force, they see a displacement, they do work equals Fs and they get an answer. Unfortunately, you can't just do that. As we said in one of our first slides in this section, we have to be looking at a force in the same direction as our displacement. In the case of this person, he's lifting this case F in the y direction, while he might be moving in the x direction. We cannot put this force, this y force here, with this displacement in the x direction, this s. This F and this S cannot go together. F and S must be in the same direction, say work equals force times displacement. So in this case, if he's moving at some constant velocity here, and we're looking at F moving, just being upwards, we cannot say this F times this S. So a force 90 degrees to your displacement does no work. This is a case where you cannot apply work equals F, this F especially, times this S. And other situations are, say, against immovable objects. This is very similar to the weightlifter problem. If we say hit a wall but keep applying a force to that wall, if the wall is not moving anywhere, the whole system is stationary. He might slip and then hit some final position where his velocity essentially is 0, but here in a case like this, as long as there's no displacement, work equals F times S which is 0. In this case, S being the opposite direction to his F. And often, this means if you're going to take work and calculate it as Fs, you have to look at what's referred to as a path integral. This means we have to look at our force that's pushing our object over some distance and how it changes our kinetic energy. And what that means is if we have an object that's moving and we apply a force F to it, it can follow a complex path for a number of reasons. Say it's fixed to a track and gravity is acting in one direction, or we're looking at a particle with a magnetic field in one direction which is pulling or attracting it. Here we'll have our force F, but we could have this sort of inverted S path to our particle. Now what we would have to do in talking about a path integral is look at the direction of each element of this particle's motion, and at each element say, well, for this small distance delta L, what was the angle theta between the force and the direction of displacement, and essentially sum over the entire path. What that usually means is you're taking F as a constant value, and then you're looking at this in terms of a path integral d of S or dl, one of these little distance elements. But essentially the force will push over some distance and change the kinetic energy. So the vector, the displacement vector, could only be F times S, say here, where theta essentially is 0 and F and S are in the same direction. That means if we're looking at, say, the work done by something like gravity, which is usually the case, we can take our particle and have mg acting down, and then we can look at the path of our particle. If we actually conduct this path integral, what we'll end up with after we've summed all of these little these little length elements is we will end up with the work done by gravity here to be negative mg delta y. So the force pushing over some distance will change our kinetic energy, and this is the work done by gravity. mgh, essentially, the height is often how it's written, or in this case mg delta y. All that matters here in terms of our force and our displacement, as we saw with the man carrying the case, is here's our force of mg and here's our overall displacement delta y in the same direction as the force. All of these other elements which are not in the same direction will essentially give us 0. So let's take a look at a couple of problems. Here we have a block. It has a weight of 15 newtons. So remember, this is already mg, and it's sitting on a frictionless, I know it's unrealistic, but we're going with it, inclined plane with a theta of 23 degrees. A force F here, essentially from a rope or some other device, is applied to this block parallel to the incline, so in the block's x direction, of 5.86 newtons. That's sufficient to pull the block up the plane at constant speed. So there's a few things being mentioned here. We have a force, we have theta, we have a weight of the block given as a force already, and we have the block moving at a constant speed. The question here is, what is the total work done on the block by all these forces if it moves a distance of 3.4 meters up the incline? So now we have a displacement along this incline. There's our values, there's our situation. Do you see the trick yet? There's a trick to this one. This block is being pulled at a constant speed. So often people will do long, complicated calculations to prove this particular problem. But the key point here is it's moving at constant speed. If we include only the work done after the block's been moving at constant speed and not the work needed to start it moving from rest, which is what we're going to do, then the block travels at constant velocity. This means that F in this case cancels. If F cancels, A cancels. So work equals F times S. This means we only end up with our displacement here. So in terms of kinetic energy, we won't see a change. Work done for our system at constant speed will be 0 joules. So let's change it up a bit and look at the work again, this time from the perspective of what is the work done by gravity as the block moves up the incline. Now I want you to be really careful here, because the problem stated in the previous case it had a weight in newtons, and people frequently mix up work here with a weight. This isn't weight due to gravity acting on it, this is the work done by gravity, and that again, as I like to point out, is one of the common problems. So we were at angle theta again. What's the work as the block moves 3.4 meters up this incline? And don't fall for what I consider to be one of the obvious traps that we discussed from a previous slide. Well, work essentially is force times distance. The force that's acting on our mass is negative mg downwards, and we're moving in the y direction. The only thing that makes a difference in terms of work here is the y direction and mg. Gravity is acting down. So all we care about is what is the upwards displacement of the block. That means we need to find the y component of the block's motion up the slope. We cannot put 3.4 here with our 15 newtons essentially. So we have to take 3.4 sine of 23 to project our distance onto the y-axis here, and we will find that we end up with a 20 newton or 19.9 joules, not newtons, with 20 joules-ish value. So the key point here is we can only use the y component of the block's motion. And like I say, a common problem here is people saying 3.4 times mg are 15 newtons. That is not the case. Why is the work negative? Well, here, this is the work done on the block by the force of gravity. And you have to be very careful as what is the work being done on the system or by a system, and that changes the sign. So here we're saying now that the situation is essentially the same, but now what is the work done by the normal force as the block moves up the inclined plane? Well, our normal force, remember, is a force coming out of the top of this block. The top of this block. We have our mg downwards, but normal force comes out here. It also comes to mg cos theta, remember, for our inclined plane system. Direction of motion is this way, n is this way. That should lead you to the conclusion that the normal force for this entire length of travel is 90 degrees the direction of motion. So the system does no work on the block. So 0 joules is our answer. So questions are often posed in such a way as to say, here we have a taxi driving up a hill with constant speed. Which of the following statements best describes the total work done on the car by all the forces as it moves up the incline? And this is a typical kind of question you see on professional exams, such as in MCATs and such. Well, the total work here, of course, if we're saying the total work done by the car, constant speed, as per the previous problem, will give us a total work of 0. So essentially an exact repeat of a previous question. Make sure you can justify to yourself why this is the case. Now we could see situations where you have a lot of forces involved. So here we have mg, we have n, we have some tension in this rope that's pulling this block upwards. If this is the case, then work is still delta ke, But if you have many forces, you do have to say, well, what's the net force of our total system? What's the net force of this whole system? And that means looking at the work done in each case and then adding up the work that's done by each force. And also, of course, looking at their individual displacements to see if indeed any work is done. So we've discussed the idea of work here at length. Well, one of the things we also want to talk about is, to go with work, power. So we apply work to something. This obviously does not happen at one particular moment in time, and we have to bow to causality and say that we have to apply our work over some time. That means we can look at the rate at which work is done. The rate at which work is done is referred to as power, and it's often a misused term, power. But here in physics we're going to say our average power is how much work we've done divided by time. How much work we've done divided by how long it takes to do it. So if we think of work as some displacement, we can say power is how much work we're doing per unit time, or F ds by dt, or an odd way of expressing it that you may not have thought you'd see, which is a force multiplied by a velocity, as ds by dt is the change in displacement here with time is v. So this is an unusual kind of expression here for power being F times v, but this is actually dimensionally correct. So that means in terms of power we get a unit that I'm not a particular fan of, which is the watt. And 1 watt is 1 joule per second, or, because we're looking at the nature of the joule here, 1 kilogram meters squared per second cubed. So this essentially is force times distance in terms of an energy. Now, something I do want to point out here is I kind of like joules per second. We deal with things in meters per second and meters per second all the time, and don't apply any special values or say names of a unit to things like acceleration or velocity, and I'm quite happy dealing with joules per second, and quite frequently, especially on some exams, I might leave things in joules per second. The reason I don't like the watt is because, okay, they wanted to name joules per second, but the problem is watt is W, and the context we use watts in is often involving power and work, which gives you a W for a unit and a W for a variable, which I find kind of confusing. I understand watt did a lot of work into work, and involving power and involving steam engines. Watt was one of the pioneers of the early days of steam, but I kind of don't like having this extra W kicking around. It's entirely up to you if you use the watt. I will not penalize you, don't take it personally, but I like to use joules per second. That way, when I'm working at 3 in the morning, I don't sit there going, why am I multiplying my work by some factor? And then you realize that you're actually looking at a watt. So please be careful of W not being work here, but being power, a watt unit. So power is basically energy per unit time. A 60 watt light bulb uses 60 joules of energy every second. So a kilowatt is a unit of power. A kilowatt hour, however, if you go and look at something like a electricity meter, is a kilowatt, essentially energy per unit time, multiplied by time to give you an energy. Why they don't just simply calculate these things in kilojoules, I don't know. It's probably because they can put it in terms of hourly usage and then charge you, even though you're not really using any power other than your fridge. So that's the kilowatt hour. It's a unit of energy. I won't ask you to do a calculation with this, but if you see this in terms of, say, your home electricity system, that's actually telling you how much energy you've used. It's multiplying unit of power by time. You often also see, if you talk about engines, if you go and look up the latest specs for a car or outboard engine or something like that, you see things quoted in horsepower, which tends to be more of a mechanical engineering unit, and it's still in common usage today. 1 horsepower is the inconvenient conversion of 745.7 watts. Why we can't use essentially joules per second for all of this and just dispense with it, I don't know. But the horsepower still exists, and you can find, of course, quotes of power for engines in terms of horsepower. So, in terms of our calculus, our power, of course, will be dW by dt. So if you have a function in terms of power, you can do differentials. If you want to find the work done, of course, you can look at integrals of the path, and you can figure out any value you need. So let's take a look at power. Here we've got this little guy. He's driving an airboat. It has a total mass of 3.5 times 10 to the 2 kilograms. He's going to speed up in a straight line from 27 meters per second to 34 meters per second. So we have a VF, a VI, and a mass. What is the power of this boat's engine? So here's what we have to play with. We have M, we have VI, we have VF. So our initial kinetic energy essentially is going to be half mv squared, KEI, or KI as I've written here. I tend to use KE wherever possible. I deviated from my own rules here. So the initial kinetic energy is 3.5 squared over 2. Sorry, 3.5 times 10 to the 2 over 2 times 27 squared, more accurately. This will give us essentially 127.6 times 10 to the 3 joules, about 128,000 joules. Our final kinetic energy will simply be the same again, 175, but this time multiplied by 34 squared. If we do this, we'll get about 202,000 joules. So our simple calculation then will be that our work is equal to the change in our kinetic energy, which will be 202.3 times 10 to the 3 minus our 127.6 times 10 to the 3, giving us an answer of about 74.7 thousand joules. 74.7 times 10 to the 3 joules. But this is the work done. Here we're looking for the power. Here's our work done. Well, remember, our power is essentially our energy over time. Let's say it takes 6 seconds here. This will be 74.7 times 10 to the 3 over 6 seconds, which will give us 12.45 times 10 to the 3 watts. Let's take a look at another problem. Here, and this is based on some personal experience being projected onto the salesman. Traveling salesman has been sitting in an airport bar in Chicago O'Hare Airport, an airport that's very difficult to get out of in the winter, as I found by personal experience. And he's just realised he only has a few seconds left to make his connecting flight, or he's going to be forced to spend a night in a cot in the middle of a very large airport terminal. So he's going to run the 100 meters from the airport bar to the gate. So he takes his bag here, and he's going to pull on his bag with some tension T along the strap and cover the 100 meters to the gate. So he runs 100 meters to his departure gate and pulls his strap with a constant speed at an angle of theta equals 45 degrees to the horizontal. The tension in the strap is 20 newtons. So here we have a tension in the strap at 45 degrees, 20 newtons, 45 degrees, running 100 meters. And he's obviously terrified. How much work is done on the case getting it the 100 meters to the gate? Well, our force is the tension in the strap. It's at 45 degrees and he's going 100 meters. the work done will be the tension times the displacement times the cosine of theta. Work is equal to Td cos theta. Substituting in, our force of 20 newtons times 100 meters times a cosine of 45 gives us about 1400 joules of energy. Now let's say it takes the man 30 seconds to cover that 100-meter distance. He's really moving it to try and get to his flight. How much power was required to complete his journey? Well, he does 1400 joules of work pulling the case. Power is simply work over time. 1400 joules over 30 gives us 47 watts. So remember here, the things to take into account are what was the direction of the applied force, what was the direction of the displacement. Following that, how long did it take to do this work? So 1400 over 30 seconds gives us about 47 watts. Unfortunately, he reaches the gate and Stewie here turns him away. He can't go onto the plane because they've closed the door, and even though he's sitting there watching the plane, he basically has to watch it leave without him. So he walks the 100 meters back to the bar, where he'll hopefully be there until closing time, drowning his sorrows of spending the night in Chicago. How much work has been done on the case during his trip? So he went to the gate, he ran to the gate, and now he's going 100 meters back to the bar. How much work has been done? Well, work is equal to force times displacement, blah blah blah, but here we can sit here and work out F cos theta, and what we'll end up with is work will be positive in one direction and negative in the other. In other words, S, the displacement of this man, he went from the bar to the gate and back to the bar, his total displacement is an S of 0. This means he's done absolutely no work whatsoever. And since he's not going to do any work in the next 24 hours because he's going to be waiting for the next flight, he's going to spend a lot of time sitting in the bar.